Hello, everyone. This is the second What Happened Wednesday for MAE 3724 Dynamic Systems Analysis and Introduction to Control. Today, we're going to be going over stability. Stability is a condition at which x dot as a function of time is equal to 0. Typically, this function is defined as x is equal to a function of both x and u are input. This function reaches stability at an equilibrium point that we typically denote as x subscript e. If we were to start said function at xe, i.e. our x at time 0 is equal to xe, then our x dot of t would be 0 for all of time, and the function would remain at this equilibrium value. The open loop controllers we've discussed in this previous week tend to shift or move the equilibrium points in a system so it remains at this equilibrium. Equilibrium can be defined as both stable and unstable. Looking first at the unstable system, this can be easily modeled by a ball sitting on top of an upside-down bowl. Looking at these functions, x dot is equal to axe, where a is a value greater than 0. So when we give this a positive delta x in the positive x direction, our x dot will be greater than 0, meaning it will decrease down the side of this bowl. Looking at a value of a negative delta x, our x dot goes to a negative value, meaning it will roll off this side or the left side of the bowl in the negative x direction. Typically, unstable systems, x dot is pulled away from the equilibrium point when given any type of a delta x input. Now looking at the stable equilibrium points, they can be modeled by a right side up bowl with a ball sitting in the middle at the equilibrium point. Looking at the functions, x dot is equal to this axe like we have before, where a is a value actually less than 0. So when given a delta x that is greater than 0, our x dot is going to be less than 0, meaning as we increase this delta x in the positive x direction, our reaction or derivative, x dot, is going to be pulling it back towards this equilibrium point in the center of the bowl. Looking at the controversy side, our delta x being less than 0, our x dot is going to be greater than 0, where if we give it a negative delta x, it will be pulled back towards the right towards the equilibrium point. Stable conditions, x dot is pulled back towards the equilibrium when given any type of a delta x input. Everything we've talked about thus far has been defined as static stability, which is a prerequisite for dynamic stability, which is normally looked at on a time scale. Dynamic stability is the long-term behavior of a nudge, or a delta x, from equilibrium. Looking at three different equilibrium points, we see a straight unstable point that is statically unstable. We see from a delta x, the particle or ball we are looking at will move immediately away from the equilibrium as an initial tendency. Looking at a statically stable but a dynamically unstable system, the ball will move towards the equilibrium initially, but as time moves, it will get further and further away by a sinusoid. Because one of these terms is unstable, the whole equilibrium point is defined as unstable. Finally, looking at the red line, where we have a statically stable and a dynamically stable system, or equilibrium point, the ball will move initially towards this equilibrium, and as time increases, it will get closer and closer to, defining it as a stable equilibrium point. Thank you.